Okay, so here's an example, which I've already been told is out of date, and I just got this like a week and a half or 2 weeks ago off the Boston Celtics website, but I'm told that a couple of these people have like left. So anyway, let's imagine that they're there for today's. So you want to start us off here, Glenn?
For example, suppose we select Jeff.
Okay, you don't have to read each set. So now I've created the set. You notice the set has these curly the profile, right? The little curly braces. And then I've decided that my ordered pairs will be the person's name with their height right beside it. And we have 1, 2, 3, 4 people. So there's 4 sets, there's 4 ordered pairs. Okay? Is everybody okay with that? All right. This set that we've just written, let's give it the name, let's call it, say, set B for Boston Celtics, okay? That set of ordered pairs is what we call a relation in mathematics. And a relation is a set of any ordered pairs. Like no special idea about them at all. Just any set of ordered pairs is a relation. It's just very floozy-woozy out there, and you know, it's like anything, any set of ordered pairs you want to put together, it's defined to be a relation. Okay? So now I'm going to mix this up a little bit. Let's see what we're going to do with these Boston Celtics. Okay, so how about the next one? Ben? Can you read it right off of here?
Yeah. All right. The sun is
Okay, sorry, I forgot I had this piece in between. So all of the names, which were the first parts of each ordered pair, right? All the names, if we go back here and we look at the ordered pairs, the first component in each of these ordered pairs is the names of the Boston Celtics, okay? We call those the inputs or the domain of our relation. Now, before we've run into this word domain, right, along the way, and domain, remember, was all the values you could use for X where our expression had a meaning or had a value. Now we're going to be using it as what are the first pieces of our ordered pairs? What's the first component? And similarly, the heights were listed as the second component. We're going to call those the outputs or the range of our relation. Okay. Notice we only listed 6 feet 9 inches once, even though 2 players, both Jeff Green and Gerald Wallace, were listed at 6'9", but when we list the outputs, we only list it once. Just like the very first class we had this year when we were talking about the Beatles reunion, even though between the Beatles that played in Germany versus the Beatles that came to the United States, even say Paul McCartney was in both groups, but we only listed Paul McCartney once. You don't repeat. All right, now this is a visual representation of that set of ordered pairs, where in the left-hand side, I'm putting all of my inputs on my first components, which we call the domain, which is the names of the Boston Celtics. And on the right-hand side, I have my heights listed, okay? And this is called the range. Notice each player here corresponds to one and only one height. So if I look at this picture, I could look at it and say, Avery is 6 feet 2 inches. He can't be 6 feet 2 inches and at the same time be 6 feet 9 inches. It's impossible. So he has one and only one height. Jeff Green is defined to have a height of 6 feet 9 inches, and it's okay that Gerald has that same height. Okay, and Keith is 6 feet 5 inches. So this gives you the same bit of information, but it's just a pictorial representation of the domain and range. Okay, so let's switch this up a little bit. So now, instead of listing the players first and their heights second, I'm just going to reverse it. I'm going to put the heights as the first component are my domain, and the names of the Boston Celtics as my outputs. So let's fill in this picture now, given this set of data, and let's call this set of data A. Okay. So given that set of ordered pairs, what would I actually put in my little domain here? What would I actually list in here? Can someone help me out with that? What would be the first components that are in this relation? Mary, did you have your hand up? The height. So you want to tell me what they would be, how I would put them in here? 6 foot 9 inches, 6 foot 5 inches, and 6 foot 2 inches. And again, notice I don't list 6, 9 twice, okay? Okay, so now I'll use a straight line, and we'll go on over, and we'll take this, and we're going to go over to a Boston Celtics player. And who would that be? 6 foot 5 inches. Keith. If you don't mind, I'm just going to use Keith. I don't want to write the whole thing out. And what about the 6'2" guy? Avery. And 6'9", where does that go? Oh, 2. Okay, I need 2 lines. Okay. So Jeff Green, and the other guy is Gerald Wallace. Okay. All right. So here I've got this it's the end of the season, and the Celtics are the champions. Dream on. Okay. And I'm holding this big, heavy MVP award. And if you're not a sports fan, MVP stands for the most valuable player. And I'm hauling it into the Celtics locker room, and all this champagne is spraying and beer, and they're wearing goggles. And I'm told to give it to the player that's 6 foot 9 inches. So here I am. I'm looking around, and who do I give it to? Why Jeff Green and not? Well, just from, I'm just the delivery person. I know nothing about basketball. Who do I give it to? Can I tell? Is there from this relationship given here, the relation, do I know who to give it to? No. Okay. That's a problem. Okay. In mathematics, we need to be a little more certain. Okay. We need to know that if there's an input, that it goes to one and only one output in mathematics. It's fine for this to be a relation, but it's not well defined. Okay, we would have a problem here if I said just deliver the MVP award to the 6 foot 9 inch guy. Do you agree there would be a problem? Okay, so that leads us to the definition of a special relation called a function. Okay, so our work in this course will focus on well-defined relations. A well-defined relation, or a function, has exactly one output value for any input. Said another way, for each element in the domain, that's our inputs, there is exactly one corresponding element in the range. Okay, so whatever way maybe makes sense for you, whatever way we describe it, but if you had a little picture of something in the domain, there would be one line that would go from that input to one and only one output. That is called a unique output. It can't go to 2 different places or 3 different places. Okay. So let's take a look again at our sets. I've called this first relation P here, the second relation A. And at your seats with your table mates, think for yourself and then compare your work. I'd like you to answer these 2 questions right here, A and B. So what do we have here? Someone want to help us out here with what they have on their sheets? I'm going to lower. I don't know about you, but when I listen to these videos, it scares me when it starts off. It's so loud. I don't know if it's because this is loud or anyway. All right. So which ordered pairs represents a function? Which one has a unique and only one output for each input? You can go back to the visuals if you want, or you can look at each of these. So which one is, which one, set P or set H? P, okay? And if we go back to the visuals, which makes it a little easier, for each one of these inputs, there's one and only one place that they go to in the range, and exactly one place. So that's when the names are listed first. Identify which set of ordered pairs represents a relation. Both, right? Remember, a relation is just any set of ordered pairs, no special thing about it. So they're both relations, but only P is a function. Okie doke. Every relation, every function is a relation. But not vice versa. It's the square and rectangle situation. Every square is a rectangle, but not all rectangles are squares. Okay. So now I want you to try, I've given you some visual ways to represent and some sets of ordered pairs. So at your seats, I'd like you to answer all these questions here. Okay, but I remember when I looked up and I thought it said Bach, it was like B-A-C-H, and it was something like L-A-T-A or something like that, Bacalacta or something. All right, so let's take a look at these four situations here. Is this a function, the first one? Yes. And in my first class, people were a little confused because they said, but wait a minute, both Phoebe and Amy are going to 5 feet 5 inches, and that's okay, because Phoebe is defined by one and only one height, and Amy is defined by one and only one height. They happen to be the same, but that's okay. And so remember, when you represent your domain, you always have to use your little curly cues, right? So what's the domain here? Amy, Katie, Phoebe, okay, in any order you want. And the range, 3 feet 1 inch, comma, 5 feet 5 inches. Okay, so there's 3 inputs and 2 outputs. Okay, is the second one here a function? This is a little more interesting. Cameron is saying no. Shane is saying yeah. Ben is saying I think it is. They all have, Ben says, with a little smile on his face, they all have one and only one output. Each input has one and only one output. In fact, if I made these, the domain and range, into ordered pairs, what would be the 4 ordered pairs? What would they look like that is represented by this picture? What would the 4 ordered pairs look like? Someone give me one ordered pair? 0, 7, yeah. Okay. 3, 7, negative 2, 7, and 6, 7. So if we were to graph that, we'd be at 0, 7, 3, 7, 6, 7, and negative 2, 7. Those are the 4 points. If I now said that that domain would be all real numbers, not just those 4, but all real numbers, and all those numbers went to 7, what kind of graph would it represent? Horizontal line. I could then connect them with a horizontal line. And for every input, I would go up to one and only one output. So this is certainly a function. The domain is negative 2, 0, 3, 6, and the range is 7. Okay, what about the next one? How about this one, Ricky? What do you say about this one? You said yes. Do we have any controversy about that? And what about the domain? Yeah, and that's how you'd enter it in my math lab, right? Ascending order. And what about the range, Buddha? Yep, 2, 3, and 5. Good. Okay, and finally we have the last set of ordered pairs. And what do we say about this? Is this a function? No. People seem to be pretty adamant. No. I heard a real emphatic no. And why not? Here I am in my domain, and if I pick on 3, who does 3 go to? 7 and -4, and that can't happen. Nope, can't happen. It's a relation, but it's not a function. So you can also list the domain and range of a relation. So right here I'm going to say domain of the relation, and the domain is the same as it is for a function. It's all the input values, which would be -4, -3, 1, and 3. And the range of the relation, instead of the function, would be just the output values, which is -4, 2, 4, 5, and 7. So the domain and range doesn't change whether you're talking about a relation or a function. It's all input values versus all output values. Any questions on what makes a domain and what makes a range? All right, so let's see what we have next. Well, why not take a look at the graph, because most of the functions, just about all of the functions we're going to deal with, but not all of them, because you've looked at our book, and our book has relationships between categories, or and for example, they look at marijuana use for, what was it, high school seniors. That was one of the examples we looked at. Okay, so whether someone uses marijuana or alcohol, that's not a number, that's a category. So most of the time, though, we'll be looking at the sets of real numbers, some kind of correspondence between sets of numbers. So the set of all x coordinates represents the domain of the relation, and the set of y coordinates represents the range. Okay, so here we have 5 ordered pairs. So let's fill these in. Fill these in at your seats. I'm going to do it, and you do it at the same time I do it. Hopefully you were able to fill in the coordinates of each of those points. And now let's use the graph with the coordinates listed, and now list the domain. So what would we have for the domain for these 5 points? What would we have for the domain? -4, -2, +1. Everybody agree? 0. And is that how I list my domain? Will I get full credit if I do that on a quiz or a test? Oh, not brackets, the curlies, right? The curly cues. Okay. What about the range? Austin, can you help me with the range? Yeah. 2, 4, and 5. Right. I listed my coordinate wrong there. Thank you. Okay. So now the next question is, if you're looking at this picture versus a set of ordered pairs, right? Or the domain and the range picture, but you're looking at something like this. My domain's wrong? Oh, okay, thank you. -4. Okay, so if you're looking at a graph like this, and you're asked the question, is it a function? Can you tell? And if you can, how can you tell? Austin, you said yes, really quickly. Okay. Now you're changing your mind? Okay. Oh. Okay. Oh, you're saying you. I get what you mean. Okay, so you're saying, yeah, you can tell. Okay, that he answered my question. All right, so here's the question: is it a function? Oh, no, it's not a function. Okay. Can you explain why it's not from looking at the? Right, 1, the input 1, the first component, 1 is defined to go to -2 and to 4, right? So it's definitely not a function. Okay, so because 1 doesn't go to one unique place. Visually, how can you see that? What kind of visual test could you do to determine whether this was a function? Does anybody know? Right, right. If I take a look at any vertical line and think about this as a sweeping, we're going into animation now, where you start sweeping across this graph, drawing as many vertical lines as you can. So I'm going to just start drawing vertical lines across this graph. And I'm just going to use my integer values because those are convenient. I'm going to go through all my x, not that one. Okay, and now when I come to x equals 1, I notice that this vertical line hits those 2 points. And that says you don't have a unique output for x is 1. You've got 2 of them. So we can formalize this now with what we call the vertical line test for functions. If any vertical line, and this is a key, any, you don't just say a vertical line. Any vertical line, as you sweep across your graph from left to right, if it intersects the graph in more than one point, it's not a function. So that's how you can visually get a quick hit of a relationship and do a quick visual and determine whether it's a function or not. So this first curve here, we don't have the equation for it, but this first curve, as I start to sweep across with vertical lines, I notice that my vertical lines only hit that graph in one spot, so it's a function. But this second curve, right? The second curve, all I have to do is find one vertical line, and here it is. That hits it in 3 spots, so it's not a function. So what I'd like you to do now is at your seats and verify with your neighbors. There's a couple of interesting little graphs here. So verify with your neighbors after you take some time. Use the vertical line test to identify which of these graphs represent functions. Okay, so I didn't mean to create like any little spats in the classroom here. People are still arguing about B. There is one table that differs from all the rest. Table 3, well, you all agree that this is a function, and you all agree that this is not a function. Let me just point out on C that if you simply said the vertical line test was a vertical line, right? And I chose the y-axis here and went down, it only touches it in one spot. So that's why you can't simply say a vertical line, all right? So we're all in agreement that C is not a function because it hits the vertical lines. Many of them hit that function. There's an infinite number of vertical lines that will hit that in 2 places, whereas all the vertical lines in A only hit it in one spot. So B is the one that's a little interesting, and maybe some of you haven't seen this type of function before. We're going to be studying this next week on Friday, I believe. Can you see how this graph has 2 separate pieces, right? And so each piece, this piece here, has a unique equation that's defined for all numbers less than 2. So for all numbers less than 2, I have an equation. Once I become the number 2, I have a different equation, okay? This equation, to me, looks like a cubic. And this equation looks like, well, it could be many things. It could be a quartic or a parabola, it could be anything. But the equation for the right-hand piece and the left-hand piece are different. And where the tricky part comes in is that x equals 2. So if I said to you, here's my input 2, which one of those pieces defines the output? Is it the first piece or the second piece? The left-hand piece or the right-hand piece that defines the output for x equals 2, Ben? Excuse me? Right here, because that's where the dot is a solid color, okay? So let's estimate what that value might be on the y scale. What what do you think would be a reasonable if it was one, if the scale was just our integers? What do you think would be reasonable coordinates for that point? 2 what? 2, 1, sure. 2, 1, 2, 2, those are both reasonable. What about this? If I put 2 in here, is this defined at that point? No, because it's open. So if you draw a vertical line straight down through these points, it only intersects the graph at one point that is defined, and that's 2, 1. So this is a function. Okay. If both of those places at x equals 2 had 2 solid dots, then it wouldn't be a function. Okay. So that was, I threw that in just to sort of get the wheels turning upstairs. All right. So this is a lot of writing. Okay, it's a lot of writing. So try to stay focused as it's read by Cameron after you get through your yawn.
Most of the functions will work for unless you want to work with y squared plus 1x plus 3000 y
Keep going. Thank you. Okay, so that's a lot, right? That's a lot to take in. So why don't you take like a minute or so right now and just read it for yourself, and then we'll talk about it as a class. Yeah, you could say if you looked at it individually, each one would be defined as a function, but together it's not a function. I mean, wait a minute. No, it's a function. We decided it was a function.
It's a single one, even though it's
It's a yeah, it's a function. Each piece is a function, which makes the whole thing a function. It's a good question, Shane. Never quite thought of it that way. Okay, so this whole idea, you should be familiar with this data set, right? Where did we just see this data set? In your projects, right? But on day 1, we use this equation to model the data, not linear. This is a quadratic equation. And if you recall, you could imagine a curve, a quadratic curve that might go, if you put a little point in the middle of each one of these bars, right? What you found in your project is you found a straight line that fit the data the best, all right? But you could also imagine that perhaps there's some type of curve that might fit the data that's quadratic in nature. Okay, so on the first day we were using that equation. Okay, so the variable y we call the dependent variable because it depends on the input. I can tell you from any of these models, whether we use this model, which is a quadratic model, or whether we use the one we came up with in our project, which was a linear model that was 385x plus 3,194, is that right? I think that's right. So we have actually 2 models, right? We have, and I put the little hats on the y, and that reminds me that I'm predicting or estimating. It's not the actual data. And I always use the hats, okay? So The value of y depends what year I put in here, what number of years after 2000. Once I determine whether I'm looking at x equals 5 or x equals 6, I will get a unique output. Okay, so y is called the dependent. There's nothing in here that is restricting other than this context, which only, you notice this particular context, the domain for this picture is 0 through 10. But if I had this equation, there's no restrictions on this equation. If I have this story, I can only go 0 to 10 for the domain. But if I'm just looking at this equation, and this is a hint, this is a polynomial equation because all of your exponent are non-negative whole numbers. And anytime you have polynomial equations, your domain is all real numbers. Any x can go in there. There's no restrictions. Okay. So Ian Winokur, who likes to try to come up with all these little mnemonics, came up with this for dependent variable. And you know, some of you might like this and some of you might go, I got different reactions in my first class, so I don't quite know what to expect with you. Dependent, he spells D-E-E-P-E-N-D-E-N-10 to remember Johnny Depp. Because notice the dependent variable is all alone on an island, all by itself. Does anybody remember where Johnny Depp was all alone on an island? It's kind of recent, kind of. Oh, Pirates of the Caribbean, right. Well, anyway. Oh, God, all right. So the dependent variable here is y. Another way to tell is what is your equation solved for? We say this equation is solved for y. So whatever variable is isolated on one side of the equation, that's your dependent variable. So in other words, if I gave you the height of a stone that's thrown upward with a velocity of 120 feet per second from a height of 100 feet, and I told you that this is the equation for it, which would be the dependent variable here? H, the height, because the height depends on the time that after the stone has been thrown. Okay? So height is the dependent, and that always takes the second spot in your ordered pair, and time, t, is the independent. We can't control time, unfortunately. Some of us could have plastic surgery, I suppose, but we can't control time. All right, so there we go. Now, your book does this. I've never done this before in 107, but I think it's a good thing to do. Because if you look at these two equations, are either one of these equations solved for a variable? No, they both are solved for a constant. So whether we want to sometimes be able to look at an equation and decide, is it a function? Okay, so we take each equation and we solve it for y. So let's do that with this first one. So if I wanted to solve this equation, 3x minus 2y equals negative 12 for y, what would you do first? Dan, what might you do here if you wanted to solve this for y? You could, all right, let's subtract 3x because we want to isolate, yep, the variable term with the y in it. Okay, so we get negative 2y equals negative 3x minus 12. And what would be our final step here? To solve for y, get 1 in front of the y. Sarah? Divide everything by negative 2 on both sides, right? So we get y equals negative 3 divided by negative 2 is the same as positive 3 times divided by positive 2. And when we subtract a negative 6, that becomes plus 6. Do you recognize that type of equation? What's it called? Yeah, and what's that called? Linear, right. So this is an equation for a linear graph. And why is this not opening up? Let me close it and then maybe it will open. There we go. So most of you recognize this form from y equals mx plus b, where the coefficient of x is the slope of your line and b is your y-intercept. But let's take a look. You can see here that if I put in one x value, only one y value is going to come out. No matter what x I put in, there'll only be one y value. So this represents a function. How do we tell from looking at a graph? Well, hopefully, let's see, you've got to clear all this out. Let's put this in as a graph. So it's what, 3/2, so 1.5, 1.5x plus 6. And I'm going to choose my standard window, which is 6. And you see there's your graph. It has a slope of 1.5. As you increase on the x value by 1, you go up 1.5. It goes through 0, 6. Everything's kosher. It makes sense. I hate this new thing. I have to, I got to get used to. They changed the software. I told you that the other day, right? And I'm still. Okay, so I have to have that up and then open my screen. Okay, so let's take a picture. Okay, and so this kind of gives us a clue about looking at a graph. And here's a statement we can make. Anytime you have a graph that's increasing, what do I mean by the fact that this graph is always increasing? Has a positive slope, right? It's a straight line with a positive slope. So as you would move, so if you were describing it to someone, yes, it has a positive slope, which means as you move, right, from left to right, as x increases, y increases, right? The value of x increases the value of y. We call this always increasing. And if you have a graph that's always increasing at every point in your domain, then every time we draw a vertical line through it, we are only going to hit our graph in one spot. Okay. Similarly, if I change the slope to a negative, we'd have, as we move left to right, we would have a line that was always decreasing. And a line that's always decreasing, or a graph that's always decreasing, it doesn't just have to be a line, says as x increases, what happens to y? Decreases, right? And even if you had a decreasing, a line with negative slope, that would also be a function because every vertical line would only hit it in one spot. Okay. So now we come across this one. Let's do this one together. This is interesting. We have x squared plus y squared equals 16. And we want to solve this for y. So what are you going to do first here, Adam? Okay, we're going to subtract x squared from both sides. That sounds good. And now we have y squared on the left and 16 minus x squared on the left, excuse me, on the right. And we have to take the absolute value. Okay? Excuse me, we have to take the square root of both sides. I gave it away. And the square root of y squared is the absolute value of y. Okay. And what must be inside of these two brackets? We could have the positive square root of 16 minus x squared or the negative square root. And both of those would come out looking positive if they were in the absolute value. So now I plug in a value for x. Let's plug in 7. So let's plug in 7 for x. So what am I going to get for y? Well, let's see. Y is two things. So I could say y equals the positive square root of 16 minus 7. Oh, I don't want to do 7. Let's do 2. Minus 2 squared. So that's y equals the square root of 16 minus 4, which is the square root of 12, right? But it also says y isn't just the positive square root, it's also the negative square root. So now I have the square root of negative 12. So here I have in my domain 2, and 2 is going to a positive square root of 12 and a negative square root of 12. Is that a function? No. And in fact, what would this picture look like? Well, how would you input this into your graphing calculator? Does anybody have any idea how you would input that? You have y1, but you can't put a plus or minus in there. So let's see. Does anybody have any idea from maybe playing around with these in another class, how you would input that? I can't put y squared on the right side because y is all my things here are y, but that was a good guess. So how many equations are actually defined here? How many values of y? 2. So why don't you call one y1 the positive square root of 16 minus x squared and y2 the negative. So we're actually going to need to take up 2 lines here on our graphing calculator. So I come up here and I hit square root and I put 16 minus x squared. Okay? Now, depending on how long this thing is here, right? That didn't take too long. But let me show you a little trick. Like, let's suppose that was like 7 or 8 terms long, a really long equation, and you just wanted to take the opposite of whatever was in y1. Well, here's a little quick way of doing that. You come down here and you use your negative sign down here. And then you say, I just want to take the opposite of what's up there in y1. Well, where is y1 stored? You see this thing here that says vars? That stands for variables. You scoot over to your y variables. You hit enter, and you say, I want the opposite of y1. And there you go. That's the negative square root of 16 minus x squared. So now when we graph it, I'm going to go down and do something. And here's your graph. There's your positive square root of 16 minus x squared, and there's your negative square root. So the top part is all your positive values, and the bottom part are all your negative. It's a circle. And a circle definitely is not a function, because if you draw a vertical line through this graph, it hits in more than one spot. Okay, so that's kind of a cool little thing. So when you're solving these equations for y, hang on. Now, when you're in the habit of doing something, oh no, I've got 2 of them. Okay, that's when you're in the habit of doing it one way, it's hard to change sometimes. Okay, so let me hit this. Okay, you got the idea, folks. It's a square, a circle. Oh, I don't know. What did I say? What order do I have to do it in? I thought I hit this first, and then I call this up. No. Yeah. Okay, there we go. Now if I hit that, there we go. All right, I have to have that up. All right. So there's our circle. This is how you represent. This is the picture for this y equals plus or minus. So someone said in my other class, well, every time I see a y square, aren't I going to get a plus and minus? Yeah. So that's like a little, hint that when you solve an equation that has a y square on one side, for y, you're going to get a plus and minus on the other side, which means you'll have 2 values of y for each x. So that won't be a function. Okay, so this is not a function. Okay, so the last thing we have to do is, how do we represent functions? Okay, we can represent functions verbally, numerically, which is using a table, graphically, which is a graph, and am I spelling those correctly? And symbolically, which is with an equation. Okay. So here's a representation of the heights of a baseball represented in feet for various times and for various times. Okay. So this particular table only has a domain that goes from 0 to 5. Could go out further, but right now we're just looking at values from 0 to 5 every half second is the increment, right? And then we have the heights that are associated with this. But we have a special way of representing functions. We don't use the y value anymore because we want to have something that really kind of hits home that the height of the baseball really depends, is really a function of the time. So we use these letters, little f, little g, little h, and sometimes we use big letters, big F, big G, B, H. These are sort of the common letters that we use. And we represent y now. Instead of using y, we use this notation, f parentheses x close parentheses. And we read that as f of x, okay? It doesn't mean f times x. That's not what that notation means, even though earlier in algebra, you learn that when you have parentheses, it means multiplication. This is read f of x, where the stuff that goes in the parentheses is your input. That's your independent variable. Independent variable. And the output is your dependent variable. Okay? So for this particular example, what goes into my function is time, and what comes out of my function is height. Some people like to think of this like a function machine. So here's our function f, and what I put into f is a time like 4, and what's going to come out when I put 4 into my machine is the height 67. And I can put any one of these values into my machine and get an output. Okay. So this is the notation we use. And so let's take a look at how we would evaluate this. So we read this as f of 2. So this is asking, what is the output of my function when my input is 2? And the 2 represents 2 seconds. So I go up and look in my table and I find 2 seconds, and that's right here. And as an ordered pair, that would look like this, 2 and 99. Because time is independent and the height is dependent. It depends on the time. So what do I write here for f of 2? It's the same thing as your y value. What would I write here for f of 2? 99, right. Okay. So if I now asked you to interpret this point, 2, 99, and this is where, if you've been taking a little snooze during class at all, I want you to pay attention, because some of you did not, on your project, when I asked you, or we asked you, Caitlin and I asked you to, what does a particular point mean, interpret it or explain it, some of you left out some important parts of that. When you're asked to represent a point, your sentence must include the value of each of those points, some words or value of those each of the coordinates, and the units. So here, 2, 99 has no meaning if I just write that down on a piece of paper. However, in the context of this table, 2 and 99 have very specific meanings. So if I ask you to interpret this point, you would say something like this. It doesn't have to be exactly like this, but you could say the height in feet, or you could just say the height, and then we can put the feet on in a minute. There's a lot of ways you can say this. The height of the baseball is 99 feet after 2 seconds. You could say after 2 seconds, the height of the baseball is 99 feet. There's a zillion ways you could write that. But notice, this sentence has a 2 in it, this sentence has a 99 in it, and it has the units. And I'm also stating what's going on in here. Okay? So you've got to be very clear and very specific when you write a sentence. So when you have project 2, and I ask you to explain what a point means, this is what we're looking for full credit. Okay. Now on this project, if you did it 4 times, I only took off for it once. The next project, it has to be correct. Okay. So any questions on what we mean when you're asked to interpret what a point represents? I know one of my 106 students, and I know Ian because we did the same thing last year. We did this over and over and over again to try to get this idea across. But I know a lot of you came into placement tests, so I don't know what your previous teachers asked you to do. What about f of 0? What would that be? 3, okay? Now this one is kind of interesting to interpret. How would you interpret that point in everyday English? When the ball is thrown, or hit in this case, right? I think when the ball is hit, But we don't really know whether the ball's thrown or hit. Maybe I didn't give you, what would you say after that? It is 3 feet high. Yeah. So when the ball is hit or thrown, talks about at the instant this recording starts, right? Some people say, well, can I say at 0 seconds the ball is 3 feet high? Absolutely, that's kosher. The word that we use anytime our input is 0 and we're talking about time, the word that we often use in mathematics and if you take physics when you take calculus is this, the initial height. That word initial means at time t equals 0. The initial height of the baseball is 3 feet. Okay. So the next one's a little different. Next one's a little different. Take a look at it for a minute and see what we would put for an answer. Just take a few minutes to look at it. So do I come up to my chart and look for 103 as my time? Why not? Huh? Yeah. Yeah. What is 103 here, Shane? It's the height, it's the output, right? So this is saying, hey, at what time is my baseball 103 feet? So now you look along your top row here. So oops, there I go. There's 103 right there. Okay, there it is. Here's 103. And the X value is 2.5 seconds. Okay, so here X would equal 2.5 seconds. All right. So to interpret this, you could say, my baseball will be at a height of 103 feet at 2.5 seconds. Yeah, over here, thank you. I'll fix that after class. My baseball will be at a height of 103 feet. Notice the number 103 with the unit at 2.5 seconds. So I can see both coordinates and both units. Okay. All right, so that information in this table comes from this function, this equation, okay? Our domain, because this has a story to it, our domain starts at 0 and it will end when the ball's on the ground, which we don't have that data point here, okay? But if I just gave you this equation and asked you what the domain is, you look over here and you go, oh, this is a polynomial equation because I have really nice exponents, no negative exponents, no fractional exponents. So there's no restrictions on the number I put in here. I can put any number in for X, but our story limits us to start at 0. Okay. So if we didn't have the table, but we had the equation, we could still answer this same question. What is f of 2? And how you do that is you say everywhere on the right-hand side that I see an x, I'm going to replace it with 2. So you put a 2 in to your equation where you see x, and then you simplify. Negative 64 plus 163 is what? 99. Yes? 99. Okay. And it does agree. F of 2 equals 99. That's what we found a few minutes ago from the table. To answer this, notice how I changed my language. Use the equation to solve. Up here I said use the equation to find. Here I'm saying solve an equation. So f of x, remember, is replaced by 99. So here's 99 is the output. And from here, you guys, I'm not going to take the time to do it in class, but this is a quadratic equation, and you all know how to solve quadratic equations. You going somewhere, Ricky? Oh, okay. All right. And does anybody know how you could quickly solve this without the quadratic equation? What you would do? you saw something like this on your test Friday? What did you write on your palm that I told you about? You can factor it. What's the first form of factoring I've been trying to get you to always look for? GCF. And if you pull out a negative 16 here, you get something that's very easy to factor. Negative 16 is, you could divide both sides by negative 16 if you want. Negative 16 is never going to equal 0, so you can quickly factor this. And there are your answers at 3 seconds and 2 seconds. Your baseball is going to be at 103. So don't forget GCF on Friday. It's a really nice thing, even when you have quadratic. And finally, you can have a graph. I can take that equation and I can graph it, okay? So we can use the graph to evaluate f of 4 as well as the table or the equation. Now, this is the best I could get for the graph, so we're going to have to cheat a little bit and go back maybe because I couldn't make this any bigger and still fit it on your page at that point. But where do you go? Could someone tell me, like, physically what I do to find f of 4, what I do on my graph to find that point? How I move? Here I am. I'm a little robot right here at the origin. Can you tell me how I move to find f of 4? Move over to the right until I get to x equals 4, and then what do, Adam? Huh? I draw a vertical line that goes through x equals 4, and where it intersects at 4, and what does that number say? I can't see it. You have your table right on your paper. What is it at 4? 67. So f of 4 is 67. Next one's a little different. What about f of x is 67? Can someone tell me how I walk now? I'm down here at the origin, other than Adam, to find this answer, the x value that gives me an output of 67. Where's the 67 going to be? Where do I look for that? On the vertical axis, in this case happens to be the y, and I come up to where I think 67 is, and now I draw a horizontal line across, and I notice that I intersect at 2 places. And what are those 2 places? 1 and 4. So when x equals 1 and 4, I'm at 67 feet. So we actually finished 1 minute before my 8:40 class. And I would like to tell you something now. Please write this down. Friday you have a quiz. There'll be no homework on Friday. Test, thank you. But right here, this exploration is due on Monday. And I will remind you again on Friday. This is due on Monday, so, and the answers are actually given, so if you have trouble, you can look at the answers, but I want you to work through this before Monday's class. Good luck studying. Don't forget, you have that study aid on Moodle. You have a study guide on last week's packet. You have the Math Center, the Math Studio, and you can see me if you have any questions. Good luck studying.